Oh yeah, Mr. Haverly, you need to record.
Thanks, Max. Yeah, it's not like there's 4 people in this class missing.
You only went over the notes, it's fine.
Only went over the notes. You know what this means, right? I have to sit here. I'm recording now, so they're gonna hear this rant first. I have to sit here afterwards and I have to do the whole thing again by myself before I can go home on a Friday. That's what that
I
means.
mean, you don't have to.
Yes, I do. I don't think you understand. We watched a movie in Regents this week. My entire life is this AP exam right now. I go home, I write AP problems. You guys online, let me know when you've got your answers. Same for you, Zach.
Good first one.
Do you mean this, A, B, C,
Yeah.
or you done with all 3 of them?
Yeah.
Okay, cool. You guys online, let me know when you're done with A, B, C for this problem that's currently being shared on the board.
Okay, I'm good.
Brianna, how are you?
I just finished.
Okay, perfect. So going over this one. This one highlights a bunch of key ideas that I really want to point out. Obviously, this kind of problem is a little simpler than some of the crazy ones you might see on AP. Oh, the graph paper is nice. Anyway, so for forces, there's the obvious one. There's FG. Now here's the thing. How big should I draw my normal force arrow? Yeah, it should be smaller, noticeably smaller than FG. Why is the normal force reduced in this one? Ask the Zoom people online.
Because it had part of the applied force is going to add to it, and be the same as the force of gravity.
Yeah, so normally if a block like this is resting on a table, normally normal force equals gravity. But in some cases where you've got something either lifting up or pushing on the block, the table's either going to have to work harder to keep it from going through or work less hard. In this case, since this force is taking some of the weight off of the table, the normal force is going to be smaller. And then lastly, there's going to be some friction force. You don't know how big to draw the friction force. Now, to calculate the normal force on the block, that is a force in the y direction. That means we want to find the net force in the y direction. So we're going to add the y component of our force F. I'm literally just calling it F. We're going to subtract off our force of gravity, and we're going to add in our normal force. So that's adding positively all the ones that are going up and subtracting all the forces that are going down, which is just gravity. Now, this should be equal to ma, but what is the acceleration of this block in the y direction? 0. The block is literally just going to remain flat on the table surface. So therefore, this becomes 0, and I could rearrange this algebraically to get that normal force is equal to force of gravity minus the Fy, which makes sense. It's saying normal force is equal to the force of gravity minus whatever component here was taken away from it, which makes a lot of sense. So we'll have mg minus F, which is that 10 newtons. And then in order to figure out the Fy, I need the opposite side of my triangle. So I'll take sine of theta. All right. So plugging in everything I know, 4 kilograms times 9.8 minus 10 times sine of 15. Therefore, my normal force is going to be 36.6 newtons. So N equals 36.6 newtons. Okay, good. So I'm going to clear this because I'm out of room. Okay. And then we want to calculate the acceleration of the block. Well, the block is going to accelerate in the x direction. I think it's this way, but we honestly don't know yet. So we want to add up all of the forces in the x direction. And we'll set that equal to m times a. Our goal is to solve for a. So we're going to have the x component of our force minus our force of friction. And that should be equal to m times a. So if the force is like this, going up, we want the x component of that force, which is going to be f cosine of theta in order to get the adjacent side from our angle. So this is going to turn into f cosine of theta minus u, which I gave you in the problem, times the normal force, which we had last time, 36.6. If I add in just a couple more periods, 36.6 newtons. That should be equal to m times a. And so we've got 10 newtons cosine of 15 minus 0.18 times 36.6 newtons. All of that comes together, and I have to divide both sides by the mass, which was going to be 4 kilograms. If there's any room left at all, very close, almost there. What is happening? Oh my God. There's nothing I can do. The answer is 0.77 meters per second squared. That's the acceleration of the system. Good. All right. So we got time left. The next important one I want to do, I'm not sure where everybody is on this one. Zach, I know, was trying to speed run all of them. Yep. I want to do the last one. I want to do the one with the block, one on the ramp, one on the table. So the thing is here, there's friction on this tabletop surface. There is no friction on the incline. And I want you to derive an equation. I want you to come up with some kind of equation that's equal to the acceleration of these two blocks moving together. And the rule is your equation can only have 3 letters in it: the angle, the coefficient of friction, and G. I don't want to see any M's. I don't want to see anything else. And the main thing I'm giving you is where the friction is, and I'm informing you both blocks have the same mass. So make that equation for me. Max, you can see the shared screen, right?
Yeah.
Okay, thank you. You guys let me know when you have an answer.
I have my answer.
Awesome, Brianna. Zach? All right.
I also do.
You also do. Fantastic. Okay. So it's very common that those derive me an equation questions are going to involve the Newton's second law equation. So net force equals ma. It's almost always the basis of these kind of problems. And it's important that whenever you look at these problems, one, you have the reference table in front of you because you want to use as many, you want to have access to as many equations as possible. And you want to start with an equation that has what you're trying to solve for in it. So this asks you to derive an equation for acceleration. Check. All right, I've got an equation with acceleration. Normally, if you have no idea how to do this, if you get really stuck on these derive an equation problems, starting like this is great. If you find that it doesn't work or you get lost, you can always find another equation that has acceleration or whatever you're supposed to be solving for in it. So we're setting it up like this. So I'm not allowed to use force or mass. That's unfortunate. So I want to replace these two. So let's start with force. So I want to find the net force in the direction that these masses are going to go. And I think that this guy is going to drag the one on the table down the ramp. And so it'll be that direction. If I'm wrong, I'll get a negative answer, but I think that's the way they're going to go. And so what are the forces that are on each of these blocks? Gravity, so they both have Fg. You guys online, shout out some forces.
They both have a normal force, but they're different.
Yep, normal force, but different. One goes perpendicular. Oh, the other one also goes perpendicular. Wait a minute. No, they are different directions, but similar kinds of forces. Here they should be equal. I'm trying to not break my own rules. Okay, more forces. There are still more forces. One block has friction. This guy, he's got friction trying to hold him on the stable surface. So we got that. What else? One more. How is this block going to get pulled? Tension. We got tension. Now, honestly, if this was the problem and it wasn't draw the free body diagram, you need to draw tension for this free body diagram in order to be correct. But if the problem was give me the equation for acceleration and you forgot about tension, honestly doesn't matter because as hopefully we know, tension is going to ultimately cancel out here. But anyway, so we want to just look at the forces that matter. Okay. And the forces that matter are going to be friction, the tensions, and the FGX pulling the block down the ramp. So I'm going to actually clear off all of the forces that aren't in the direction of motion. So that's gravity, normal force won't help me, normal force won't help me, gravity won't help me. So it's just these four forces I'm dealing with that are in the direction of motion. So everything that is going in my positive direction of motion, I'm going to add. Everything that's going the other way, I'm going to subtract. So adding FGX, adding tension. And that's all the forces, this tension, this FGX, that's everything going that way. Now I'm going to subtract off tension and my force of friction. As we can see, tensions cancel out, so they were never here, which is nice. But now this is going to turn into mg for the force of gravity times sine of theta. We get the sine of theta from breaking down the gravity forces. Always like to say it. I never want anyone to go, but where did the sine come from? That's where it came from. Minus force of friction. And force of friction is going to be U times the normal force. For that second block, it'll be equal to A over M. Now, this normal force here, what's it going to be equal to for this block that's up on the table here? Yeah, so that block doesn't have the problem our previous block had. Normal force is easy in this case. Normal force is just equal to the weight, or M times G. So I can clear this out. Not normal force. We want to have mg instead. All right. Now, this is useful because we can clear off all of the m's because m cancels out. And I'm not done because I've made a mistake.
Is it 2M on the bottom?
It is 2m on the bottom because we had mass, we had both one block here and we have one block here. And so we have to remember that when we're talking about MA, it's the total mass of the system. So 2m on the bottom and the m cancels. So just making sure this is sine of theta. Yes, so it should be G sine of theta minus U times G over 2, which I liked to write all nice and pretty. G sine of theta minus U over 2. That's equal to my acceleration. Okay. Any questions for me? Okay, so at this point, we're out of time. I'm going to extend the offer I did last time. This is as long as I feel like I can keep you here. If you guys need to leave or want to leave, that's perfectly fine. I am unfortunately trapped here because I'm going to go over the final problem and I am going to rehash the notes, which I forgot to record, and then I get to go home. So if you guys want to stay for the last problem, then you're welcome to it. Otherwise, you can log off for the day if you choose to.
Have a
Zach,
good weekend, Mr. Aberley.
all right, Max, you have a good one. What is your plan? Because they just left.
I get confused on tension stuff of different blocks and different masses, so I wanted that.
Okay,
The acceleration, I'm pretty confident. So,
okay. So the acceleration on, so this pulley thing,
Yeah.
you think you got the acceleration, but what's confusing for you?
is the tension just gonna be 98 newtons?
The tension on the second one?
Yeah.
I haven't even calculated it yet. Hold on. So 9.8 times negative 6 divided by 0.2. So that's the acceleration. Okay, and so you have T2, FG3, 10 kilogram times 9.8 meters per second squared. Subtracted from T2 has to be equal to 10 kilograms times negative 2.67 per second squared. So 10 times 9.8 negative 10 times 2.67 plus second answer. What did you get?
I had 98.
No, I got 71.3 newtons. So you want to go do the last one with me? Okay. So for those of you watching the video and are very confused what's happening, we're going to look at the last problem, the pulley problem. So again, we want to find acceleration, and we're going to do that with Newton's second law here. F equals ma. Now, so therefore, we want to get the net force in our direction of motion divided by our total mass, so mt, I'll call it, and that will give us the acceleration. Now, the net force here, we want to look at all the forces that are in our direction of motion, which on a pulley system like this, that's all of them. So we have Fg for this first block, and then we have tension. And then for the second block, we have tension going this way and Fg here. Then we have a different tension, which I will draw with a different blue arrow. Those are my tension forces. And then we have an Fg here as well. Okay. So the free body diagram gets kind of confusing, but I'm about to list them all out. So all forces that are going in the positive direction that I chose, so I chose this to be the positive direction. We have Fg for that first 8 kilogram block, okay, minus tension. Okay, I'll call this T1, which is going to be the same as this T1 because it's the same row. So minus T1 plus T1. So we're subtracting this first tension because it's going the opposite direction, and we're adding this tension because it's going in the same direction as motion. Then we're going to subtract second gravity, Fg2, and then we're going to, are we adding tension? No, we're subtracting it first. So subtracting T2 plus T2, and then lastly, minus Fg3. So a lot of forces. And then we're adding up M1 plus M2 plus M3. So the total mass of the system. So the tensions all cancel. T2 goes away, T1s go away. That just leaves the Fg's and the masses. So I'm going to write it again up here just to make sure no one can see it. So M1 times G minus M2 times G minus M3 times G. I'm going to make this clear. 1, 2, 3. At this point, my diagram is ridiculous, but I'm trying to make it clear. First block is the one on the left, then 2 and 3 on the other side. So all of that divided by the sum of M1 plus M2 plus M3. Okay, so that's going to turn into this. G times 8 minus 4 minus 10 divided by 8 plus 4 plus 10. That'll be my acceleration. So I plug in 9.8 for my G, and I get an acceleration of negative, because I picked the wrong direction, I guess, negative 2.67 meters per second squared. So I found the total acceleration. Zach, how do we do on that?
Yeah, that part's fine.
That part's good.
Second part.
Yeah. So this part is not bad because you do the total of everything. And if your answer comes out negative like mine did, that means instead of this direction being where it's going to go this way instead. So that's the actual direction that they're supposed to be going. But I don't have to change anything. As long as I stay consistent, then say that that direction is negative, then I'm fine. Right? So I'm going to clear this off, but I'm going to record the acceleration I have because that's going to come in handy. Acceleration for the system was negative 2.767. Now, these problems typically ask you solve something really big in general, like the acceleration of the whole thing. And then they'll ask you something specific. So they asked you for the acceleration, then they asked you for this T2. And so what you want to do is you want to change gears. You start with looking at the whole system. Now you just want to look at one block. So you know how like I can choose the bar in our AP problem this week to be the system. Now I'm choosing this one block to be my system. So I'll set up net force equals MA again. What are the forces on my block here? Tension and gravity. So I'll make tension positive because I decided that that was the way things were going to go this way. And then minus FG3 for the weight of that block. And this would be M3. And then what's the acceleration that my block's going to actually move with? Yeah, negative 2.67. So it has the same acceleration as the whole system because it's attached to it. But now I know everything else. So T2 minus M3G is equal to M3 times that acceleration. All right, so I can plug in 10 kilograms and 9.8 equals 10 kilograms times that acceleration. Minus. There we go. And I can solve for T2. And in this case, my T2 came out to be T2 equals 71.3 newtons. Zach, let me know if you agree. I might have made a math error, but I don't think I did.
The acceleration. So I think I had it the opposite way, so then it's gonna have to be FG minus still, I think, right?
Yeah, so your acceleration is going to be positive,
Yeah.
right? And then your FG is going to be the positive one, and your tension is going to be the negative one. So if you pick the opposite direction, everything's going to get multiplied by -1, essentially. And so all the signs will be different, but the equation will be the exact same setup.
You said 71.3.
That's what I got.
No,
All right, so Zach, that's the general rule. You want to solve for the big thing like acceleration, adding everything together. And then when they ask you for something specific, look at the least amount of stuff that's affected by it. So in this case, this last block, I could look at this one, but this one's got more things going on. So if I just look at that one block, it's just got T2 and a gravity I can calculate.
I
This
wasn't
one, there would have
thinking
been
of
3
that.
forces and it would have been harder.
Okay.
Yep. All right. I have to go through notes. I literally have to teach and no one's even here.
So what you were doing at the beginning, yeah.
Yeah, basically. Not this one. How's everything going so far?
Good. We're getting there.
Good.
All right, thank you.
No problem, Zach. You have a great weekend.
You too.
Work on that AP problem.
Oh, of course. Highlight of the weekend.
Oh, I know. Okay, where is notes I went over? Did I close it? Not very helpful for you guys. Okay, there we go. Okay, so for those of you watching the video, I did you a disservice and I forgot to record for the first part. So I'm glad we went over all the problems, but now I want to go through the notes. So the dynamics notes start here. Okay, so these are really blurry force equations, but it's just F net equals MA and the force of friction equation. Notice the force of friction equation is equal to or less than U times normal force. We'll talk about that a little bit more at the end. The easier versions of these equations don't have that. The easier versions just have that the force of friction is equal to U times normal force. I'm going to explain why that's not always the case at the end of this presentation. Dynamics is a complicated unit with a lot of different ideas, but luckily for us, not a lot of memorized equations have to be done. Most of the work we're going to deal with is just A is equal to net force over M. So let's chat. Free body diagrams, it's kind of a big deal. So I'm just going to go through the rules of drawing a proper free body diagram again. So you want to start your pen or your pencil on the object where the force is applied. So basically, if it's FG, you want to start in the middle and draw an arrow in the direction of the force. Sometimes if like there's force of friction with the surface, you want to start on the surface and draw that way. But that's the basic idea. Your force should start on the object and then move in the direction of the force. Never do anything like this. That doesn't really work. Now, draw an arrow in the direction of the force. Number 3, the length of the arrow communicates the magnitude of the force. So an example would be if an object is accelerating to the right, because there's a really big force going this way, and there's a very small force of friction, you want to draw that with your arrows. So force of friction is a tiny arrow, and the force pulling it to the right is a big arrow, okay? So magnitude, remember, is how large or the actual number associated with the force. So you want to make sure the larger the magnitude, the larger the force arrow. And then lastly, forces often have components, but they're not required for free body diagrams. Yeah, so they ask you for a free body diagram and say, for example, the free body diagram is on an incline, like in this case, okay? You'll be very tempted to draw all the forces and then in the same way we did in class to break down the gravity into its various components, which is totally fine, except they're often not asking for the components. And so you potentially getting the components wrong is not a way you want to lose points on the exam. So you only really draw forces unless they specifically ask for the components, but the components are not necessary. Now, there are 2 ways to find net force. You want to either A, add up all the forces in the direction of motion. So remember, if there's an object and it's got lots of different forces, you only add up the forces that are in the same vertical or Y direction or X direction as the direction you're currently adding up. So there's going to be net force in the X or net force in the Y or whatever direction you're adding. You can't mix match them. So you can't add a Y force to an X equation. It's not really going to work out for you. You have to pick a direction of motion that could be X or Y, or it could be whatever direction the objects are moving in the problem. And you want to add up the forces in that direction. You don't want to add up other forces that are going in different directions. Now, if they do not give you enough information to either calculate the forces or they don't give you enough information to algebraically solve for the forces, then the only other way to get net force is to have the total mass of the system and multiply it by the acceleration of the system. Okay, so those are the two ways. So you're either looking to add up the actual forces, or you're using m times a to get the net force. So this has a lot of information on it, and a lot of these slides do. I don't want you to get overwhelmed. I want you to just think about what each little thing means. For example, this is net force in equilibrium. This idea of equilibrium, when all forces balance on an object, it's in equilibrium. So that doesn't mean that the object is still, that just means that all the forces add up to 0. So an object that is in equilibrium can either be not moving or moving with a constant velocity. The only thing is they can't be accelerating, okay? That's the key idea. So they'll ask you questions about equilibrium, whether or not it's in dynamic equilibrium. That just basically means, do all of the forces add to 0? If they don't, it's accelerating, it's not in equilibrium. If they do, it's in equilibrium, and it still can be moving as long as it's moving with a constant velocity. Now, there's not a huge focus on memorizing Newton's laws, but they are very useful to know. For example, the first law, a body at rest will remain at rest and a body in motion will remain in motion. This is basically inertia. Okay, basically mass, or the more mass something has, the harder it is to accelerate. That's Newton's first law. And it's a key idea that they're going to be testing. They just might not ask you what law is it. So it's an idea that you should keep in mind. Obviously, the most important law for this unit and really the rest of the class is a force acting on an object is equal to the mass of that object times the acceleration. It is a law that's literally an equation, and it's basically what we obsess over during this whole topic. Now, the last one is much more useful than the first one, but not quite as useful as the second. For every action, there's an equal and opposite reaction. So, for example, if an object is being placed on a tabletop surface, the force of gravity being pushed down on the object will be equal to the normal force, unless there are other forces at play. So that's an example of an equal and opposite force, or an equal and opposite reaction. And so these happen a lot. Another example would be if two blocks are connected by a cord, and there's a tension force on the cord. Which side of the cord, here or here, is a greater force of tension? Well, the answer is that the tension is just the same, because a rope cannot be pulled on one side harder than it pulls on the other side. The tensions have to be equal for both ends of the same rope. Again, for every action, there's an equal and opposite reaction, or in better words, for every force, there is an equal and opposite force. Similarly, you have two planets, and one is being pulled by a force of gravity. It's the exact same force of gravity pulling the other planet toward it. So the force between the sun and Earth, the force pulling the sun is the same as the force pulling the Earth, and I weigh just as much as the Earth weighs on me, and vice versa, because every action, there's an equal opposite reaction. There's going to be tons of questions asking about these, very likely. All right, speaking of forces, which I've mentioned a couple times, there's only a couple of them. So there's the force of gravity, then there's tension, normal force, force of friction, applied force, and a force from a spring, if that's possible. That's it. All the other forces in the universe are not going to be on the AP exam. Forces like the electric force, which we were supposed to talk about, but didn't actually make it to the test. So basically, this is kind of a common issue where, say I get a crazy situation, like here's two balls tied to a string. I'm going to chuck it tomahawk style, and it's going to rotate as it flies through the air. A AP question that we actually went through this year, if you can remember, is looking at one ball, this ball here. What is the they asked you to draw a free body diagram for this ball. And I often get students that are quite confused on this. They're like, okay, where's the centripetal force? And is there other forces going on? This list of forces that I've created on this slide is very useful for a very simple reason. It's a nice little algorithm to make sure you found all the forces acting on an object. So step one, is there gravity? If the answer is yes, draw a force for gravity. So I'm going to draw the ball again up here in the corner. So what's in the red box, I've just drawn up here slightly differently. So is there a force of gravity? I assume this object that I threw is on Earth or near the surface of the Earth. So there is going to be a force of gravity. So I'll draw that. Okay. Next question. Is there something touching it? So that's the rest of the forces. Okay. The only force that doesn't have to be a physical thing touching it is gravity. Otherwise, all the other forces must be in physical contact with it. So the answer is, yeah, there's only the string. So we've got the string, which is a tension force, and that's it. No other crazy forces that you have to add to this list. You know you have all the forces because you've considered gravity and you've labeled all the things touching it. Those are the only two kinds of forces you could have in any AP problem. So let's just run through the different kinds of forces. So tension is what you call a force caused by a rope, chain, or cord. And like I mentioned before, the force at both ends has to be equal. So you have T or Ft to represent tension. Normal force is Fn or just N, and it's a contact force between objects. And it always acts perpendicular to the surface of contact. Okay, so that means on a flat table, it points up. On an inclined plane, it points this way, perpendicular to the surface. Force of friction, I'm going to talk about that a little bit in a second. Force applied is kind of a general term used to represent like car engines, or some guy comes up and pushes something. It's any force that's applied to an object that's not labeled as one of these other things. And then lastly, force from a spring, which I will talk about more in the energy review session. Well, you knew it was coming, inclined planes. So the free body diagram for forces on inclined planes, you have the weight of the object, which always points straight down to the earth, normal force that's perpendicular to the surface. And if the block is sliding down the ramp, friction going up the ramp. These three forces are it. Those are all the forces, unless there's something weird, like something's pushing it or something else is going on. Those are the forces that act on an object on an inclined plane. They always like to ask, what does the free body diagram for an object like this look like? That's a very often question. Now, it's very often to draw it with components. So it's very useful to know that the force of gravity going down the ramp is mg sine of theta, or fg sine of theta. And the normal force is often equal to fg cosine of theta, unless the situation is weird for some reason. Theta being the angle of the incline, of course. All right. Now, the only ever time this gets weird is just in case they ever push the object up the ramp. So both of these diagrams are drawn with the assumption that the block is going down the ramp or sliding down the ramp. Friction is going to point in whatever direction is opposite of whichever way the block is moving. So if by happenstance, the block is going up the ramp, then gravity, or the gravity component, Fgx, is going to go down the ramp, and friction is going to go down the ramp. That's only when the block is going up the ramp instead of down. Then everything else is the same. Full Fg goes like that, normal force like that, etc. So pulleys. First off, basically don't focus too much on this box here. It's full of a ton of useful information, but it's mostly just an example problem. You can look at it some more if you want to do some studying. But in general, pulleys are just a way for them to bend the direction of motion into different lines. So normally we would have one block tied to another or an object on a ramp or something, and we could pick either left or right to be the positive direction of motion. However, pulleys just allow us to bend these lines. They don't actually change the problem. They just bend which direction matters. So for example, in this pulley, M1 is the heavy one. M2 is a little bit lighter. And so therefore, it's going to rotate in this direction. Now this is a little bit backward because M2 is going to go up, M1 is going to go down, but they're both traveling in the positive direction. That's because this line connecting the two blocks is basically the same thing as this problem, just bent. That's what pulleys do. They allow you to bend it. Here's another great example. Here's two blocks tied together, and the pulley allows that direction of motion to be bent like this. So you don't have to do anything extra. It's just going to change the way you add up the net forces. And I did examples like this in the time before going through these notes. Last slide, the force of friction. So there's two kinds of friction. There's kinetic friction, which is a little bit weaker than static friction. So typically, if they ask you which one's stronger, static friction is normally the stronger force of friction. So kinetic is whenever two things are actually sliding next to each other. And static friction is when they are not sliding against each other. That doesn't mean they're not moving. This just means there's no sliding. An example of that would be like a car tire. No sliding with the car tire, but definitely still moving. And here's the discrepancy I showed you at the beginning. So we normally just say force of friction is equal to U times the normal force, which is totally true forever and always, but only for kinetic friction. This is not true for static friction. Static friction is a little bit more complicated. Imagine this. Imagine a box resting statically on a table. If I apply a little bit of force to that box, I might not be able to move it. I might not have applied enough force to move the box. Therefore, friction does not have to work as hard as it possibly could in order to stop the box from moving. So here's the idea. If I applied this force, okay, that means force of friction only needs to be this big. There's way more force that force of friction could apply, but it's not doing it because it doesn't have to. That's why in some cases, it could be greater than or equal to the coefficient times the normal force. Because if you're not pushing on it hard enough, it doesn't have to push at its maximum strength backward. So let's up the ante. Let's push really, really big. Let's push with a really, really strong force. Something like here. That means that we're using the maximum amount of, we're pushing with the maximum amount of force that the friction, static friction can withstand. Once we go any larger than this, now we start sliding. And that's what this drop off is here. So if we ever break this point here, then suddenly the block starts sliding and friction drops. Because again, kinetic friction is less than static friction. So I can just push this block, it's not moving, push this block, it's not moving, push this block, it's not moving. Now starts moving. Static friction versus kinetic friction. And that's all of the notes. So if you guys have any questions for me, please let me know. Send me a Schoology message. I'll do my best. But otherwise, guys, have a great weekend. I'll see you later.